Hello everyone, I am Diksha Javkar and today we will be discussing about triboelectric nanogenerators, also known as TNGs. So this is a basic design of a TNG, which is a device which can convert mechanical energy into electrical energy by coupled effect of triboelectrification and electrostatic induction. So here we have connected one TNG to an oscilloscope, and as we are giving an input, a mechanical input, we can get electrical output corresponding to that. So current wise it is quite low, but voltage wise by simple tapping we can get a voltage of around 300 to 500 volts. Now it can be used as an energy harvester, also as a vibration sensor or proximity sensor. So it can be used as a self-powered sensor. So we have one-dimensional triboelectric nanogenerators, two-dimensional triboelectric nanogenerators, and three-dimensional. Also, we can design it to be flexible so that we can use it on curved surface or complex places, and also rotary TNGs, which can be used on the rotary machine to understand the RPM, to detect the faults, and we can customize these sensors depending on the need of the machine or of the automobile. Here we can modify its design as well as its natural frequency, so that the frequency range for which we want to do the sensing can be customized. Also the size and as well as its positioning can be changed. Now, to demonstrate its ability to sense the vibration, this is a vibration shaker and we have put a TNG over it. We will connect it with the oscilloscope and we will see how it will change its electrical output based on the input frequencies. So here I am connecting it and we will turn on the vibration shaker. Here if you can see, right now we are getting very minimum output. Now I am increasing the frequency. Here we are getting some mechanical input, corresponding to that we are getting electrical output. It is very consistent. Now I am increasing the frequency. Now you can see that the electrical output also increased. Here we can say that these are very good as a vibration sensor and also as an energy harvesters. Now we will analyze this triboelectric nanogenerator. As discussed, that a TNG can be made using any two materials which is having difference in electron affinity. These materials are known as tribo materials or triboelectric materials. Electrodes are given to make a conductive medium for harvesting this electricity. Now this works on the coupled principle of triboelectrification and electrostatic induction. Here we have demonstrated glowing of 60 LEDs using TNG by hand tapping it and the vibration sensing capabilities of it. Now if we talk about the working principle of the TNG, when two tribal materials comes in contact with each other, thus generate friction and triboelectrification occurs, causing the transfer of electric charge at the interface. Due to difference in the electron affinity towards electron, during electrification, tribonegative material donates the electron and reflect a positive potential, whereas the tribopositive material will accept the electrons, reflect a negative potential, which can be seen in the first figure. When the tribo materials start to separate, electrostatic induction takes place and opposite charges to that of the tribo materials get induced on the electrodes. This generates potential difference and cause flow of current between the two electrodes via external resistive load. This corresponds to formation of current peak as shown in figure 2. As the tribo materials attains a maximum separation, no current output is generated as equal potential is attained. Upon application of an external force, the tribo materials approaches each other and current flows in opposite direction between the electrodes, forming a current peak of opposite polarity. Again, the two materials make contact, triboelectrification occurs, and the cycle repeats. Hence, under repeated contact separation cycle, the TNG produces AC electrical output with positive and negative peak, generating continuous electrical energy. Now, if we talk about the working modes of TNGs, there are four basic modes. First is contact separation mode, second is lateral sliding mode, third is single electrode mode, and fourth is freestanding mode. Now, the contact separation mode we have discussed in the working principle. The two Tribo materials are kept parallel to each other face to face, and some space is given between them. They are of simple structure, straightforward to construct. They are employed in wide range of applications and are frequently designed with R-shaped spacer structure or spring-assisted structures. If we talk about the lateral sliding mode, the electricity generation mechanism of lateral sliding mode is very similar to the contact separation mode. However, it involves horizontal sliding between the two Tribo materials. Because of its large contact surface area, this lateral sliding has a higher energy conversion efficiency. A, a plane sliding structure, a linear grating structure, or case encapsulated structure are common in this. Now, in the contact separation or sliding mode, two electrodes must be connected to the load to create a closed circuit. This arrangement is unsuitable for converting energy from freely moving objects such as walking or moving vehicles. This difficulty is solved by single electrode structure which has just one ground electrode. When friction layer comes in contact to the electrode, an induction current is produced. The current flows back to the ground when the friction material separates from the electrode. Now, if we talk about the freestanding mode, a pair of symmetrical electrodes are positioned beneath the dielectric layer to construct a freestanding. A potential difference results from the movement of the dielectric layer across the two electrodes. To achieve potential equilibrium, electrons will move between the two electrodes. This procedure results in the generation of electric current. Freestanding mode is well suited for free rotation energy collection applications such as wheel rotation and wind. Now, these TNGs are very good for condition monitoring as these TNGs can be developed and designed based on the requirement. They can be customized as per the vibration characteristics or the sensing requirement of an automobile or a machine. Like we have discussed earlier, context separation, one dimensional mode, sliding mode, multidimensional mode like one, two-dimensional, three-dimensional, and rotary TNGs are there that can be customized. Now, for real-time wireless condition monitoring, they can be IoT enabled by coupling them with a Wi-Fi module or Bluetooth module so that data can be wirelessly transferred to a computer where it can be analyzed by the deep learning model that has been trained to analyze the anomalies, the change in the vibration signal correspond to the each faults, possible faults that can come up in any machine, so that whenever there is some anomaly is there or some change in the working condition is there or some near to occurring fault condition is being arising, so that this change in vibration signal can be analyzed and it can be detected and raised alarm. And in case if some feedback has to be provided or some action has to be taken, IoT-enabled actuators can be deployed to form a complete closed-loop system and form a digital twin. Now, if we talk about its applicability in the automobile industry, they are very good as they can act as a self-energizing, high-sensitivity sensors that does not need external power, that eliminates the need of external batteries. These sensors can be strategically mounted on critical components such as engine blocks, gearbox, wheel hubs, where they harvest the ambient mechanical vibration, convert them into precise electrical signal, and by analyzing these signals through frequency spectrum analysis, the system can detect subtle anomalies like bearing wear, gear misalignment, or bolt loosening long before the failure occurs. And the machine or the automobile has to be go under maintenance and the production line stops. Furthermore, they can be used to analyze the misalignment in the wheels or they can be used in the tires where TNGs monitor the specific vibration profile of the tire road interaction to detect the irregular thread wear or pressure loss while simultaneously generating enough power to provide for a Wi-Fi module so that data wirelessly can be transferred to the vehicle central management system. This dual capability makes TNG a cornerstone for predictive maintenance, enabling real-time structural health monitoring that enhances vehicle reliability and passenger safety through continuous autonomous diagnostic feedback. More apart from this, inside the cabin, they can be integrated as a smart surface like on the steering wheel, seat belts to monitor the driver behavior, detecting hand gripping patterns, steering angles, even psychological signs of fatigue and distraction to trigger intelligent safety warnings. Now, to demonstrate its capability to power microelectronics, here the AC signal which is being generated by the TNG corresponding to the vibration signal which is being provided by the vibration shaker. These AC signals is being rectified using a full wave bridge rectifier which is being fed to a small capacitor so that a buffer can be created. When we connected the calculator to the capacitor, here we can see also in the video that the capacitor turned on and we are able to perform some calculations, some operation over the calculator. This demonstrates that TNG can be used to power small electronics efficiently. Now we will talk about the vibration sensing capability of the TNG. Here the TNG is mounted on a air vacuum pump. Here we can see that as initially there was very less amount of signal which was noise was being observed. As we turned on the machine, it started generating some voltage signal corresponding to the frequency, and as we turned off the machine, no signal is being delivered. Now if we look at these signals, these are mixed signals, so these require some further processing. Upon applying fast Fourier transform, we are able to get the fundamental working frequency of this machine, which is 48 Hz. We can see that apart from the fundamental frequency, we are getting its harmonic. Its harmonics are of nine and first harmonic, second harmonic, and third harmonic, which are also similarly observed in the FFT of the signals curve, which is generated by the commercially used accelerometer. And to theoretically validate it, this frequency corresponds to the RPM of the motor. Now here another frequency can be observed as 100 Hz, 200 Hz and 300 Hz in both the cases of the TNG based vibration sensor and the accelerometer which is commercially used. This 100 Hz is the fundamental frequency of the vane passes. Here externally a 50 Hz signal, 50 Hz frequency is being observed in case of the TNG. This corresponds to the AC electrical supply which is being provided. Hence we are getting this. Now here we have mounted our TNG on a air heat gun where it is having three different settings. The three different settings have different temperature and airflow rate. Initially, there was very minimal signal was generating, which was the noise. As we started the machine, some voltage signal are being obtained at the setting 1. As we increase the setting, the the corresponding voltage signals are changing for the different setting of the machine. And as we turned off, initial uh, minimum signals are being generated. If we analyze this signal, these are mixed signal, so we will analyze it. Here in the setting 1 and 2, the airflow rate is similar. Hence, we have got the same frequencies as 140 Hz and its harmonics, which is very similar, which is observed in the accelerometer. For the setting 3, the airflow rate is quite different. Hence, we are getting a different frequency of 215 Hz, which is very similar, same as the accelerometer. It's demonstrate that TNGs are very accurate vibration sensor. Moving forward, we are integrating it with an IoT system so that a TNG can be able to power that IoT module as well as transmit the vibration signal generated by it. Here an ESP module has been used which transfer the data which can be displayed over our remote systems like laptops and monitor. The TNG is mounted over a vibration shaker, and we will be able to see the change in the vibration signals, change in the vibration and the corresponding in the voltage signal. As the more it was turned on, we got a abrupt change in the signal like this, and then we are getting constant frequency vibration is there, so we are getting constant voltage. As we are increasing the frequency, we are getting an increase in the voltage value, and then when the frequency is constant, we are getting constant voltage. During the turn off, we are getting abrupt signal. As we turned off, then we are getting no electrical output. So we will integrate it over a machine. On a hydraulic power pack and a piston cylinder arrangement, we have integrated two TNGs, one on the motor, one on the piston cylinder arrangement. So whenever the piston cylinder arrangement, whenever the piston changes its direction at the top dead center or at the bottom dead center, we are able to get a voltage signals corresponding to the vibration which is generated as the direction of the piston motion is changed. And if we add some load over the piston, we are getting the voltage of higher amplitude. This suggests that higher vibration are being generated. Now, if we talk about the motor, it is able to detect the working state of the motor, as well as if we analyze the data we are applying FFT, we are able to get the working frequency of 24 Hz, which corresponds to the RPM of 1440 RPM of the motor corresponding to that. Now, for real-time condition monitoring on these two TNGs, we have integrated it with the with ESP modules. As the machine was turned on, we are getting a status of machine on, and we are getting corresponding voltage signal corresponding to the frequencies and the vibration, and simultaneously we are getting the FFT of the signal. Now, if some fault is happening, some changes will happen, we'll be able to observe it over these graphs and we can detect. And if we talk about the piston cylinder arrangement, whenever the piston is changing its direction, we are getting sharp peaks at the top dead center and at the bottom dead center. We can analyze this peak and we will be able to know what is the motion of the piston in the cylinder, and on further processing we can analyze how much distance it has traveled. Now we will discuss about the rotary TNGs.
Hello everyone. Now we will have a discussion about rotary triboelectric nano generator. So as discussed earlier, rotary TNG works on the same basic principle as conventional TNG, that is one-dimensional, two-dimensional, three-dimensional, whatever we have shown earlier. So that principle were triboelectric charge generation combined with electrostatic induction. So in this design, rotational mechanical energy is converted to electrical energy instead of linear motion. So this rotary TNG operates in the freestanding triboelectric mode, which already have explained in the previous slides. So in this mode, a free moving triboelectric layer induces alternating charges transferred between fixed electrodes without direct electrical connection. So as you can see in the figures, this design is inspired by a ball bearing structure, which helps in achieving smooth rotation and stable mechanical operation. As shown in the CAD model, the structure consists of a inner ring, outer ring, support cage, and roller balls. These rolling balls enable continuous contact and separation due to rotation, which enhances charge generation. The interdigitated aluminum electrodes are placed on the stationary side, while PTFE balls act as triboelectric layer, and PLA is used as the overall structural material. On the left side, you can see the experimental testing setup where the rotary TNG is coupled with a motor provided controlled rotational input. Overall, this design allows efficient energy harvesting from rotational motion, making it suitable for applications such as rotating machinery, monitoring, and self-powered sensing. Now, I will explain the working principle of rotary TNG in detail. As shown in this slide, the working is based on freestanding triboelectric mode, where PTFE balls act as the triboelectric layer, and aluminum interdigitated electrodes act as charge collectors or the other triboelectric material. So initially, when PTFE bolts comes into contact with the aluminum electrode, the triboelectric charge transfer occurs due to the contact between two tribo materials. Due to the difference in triboelectric polarity, PTFE bolts become negatively charged while the aluminum surfaces become positively charged. As you can see in the figure 28, the positive peak generation happens when PTFE bolts moves from electrode A towards electrode B. Due to rotational motion, it creates an asymmetric charge distribution between two electrodes. This imbalance induces an electron transfer from electrode B to electron A through external circuit, generating a positive P current. As ball continues to rotate further and moves from electrode B back towards electrode A, the induced electric field reverses, and this reversal causes electron to flow from in opposite direction, producing a negative current peak, as illustrated in the next figure. So with continuous rotation, PTP balls repeatedly passes over alternating electrodes A and B. This results in periodic positive and negative current peaks, which together forms an alternating current, which is AC output, as shown in the final figure. Now we will discuss about design and fabrication of the rotary TNG. This slide shows the fabrication process and the experimental setup of the rotary TNG. The structural components of the rotary TNG, including inner ring, outer ring, and support cage, were designed using CAD softwares and fabricated using 3D printing. PLA material was used for 3D printing due to its ease of fabrication and dimensional accuracy, and mechanical stability also, which makes it suitable for prototyping and laboratory scale testing. After fabrication, aluminum electrodes were integrated into the outer ring to form the interdigitated electrode structures, which is required for charge collection. PTFE elements were then assembled within support cage, completing the triboelectric interface of the rotary TNG. Figure 33 shows the final assembled rotary TNG, referred to as RTNG. On the left side of the slide, the experimental setup is shown, where fabricated rotary TNG is mechanically coupled to a DC motor to provide controlled rotational motion. A regulated power source is used to drive the motor. Electrical output generated by the rotary TNG is measured using an oscilloscope. Overall, 3D printing enables rapid fabrication and easy modification and repeatability, making an effective method to developing, testing, and rotary TNG prototype. So, in this video, you can see the rotary TNG in working. And as you can see, when I turn on the rotary TNG, we will have a signal occurred in the oscilloscope. As you can see, when the rotary TNG is turned on, the signal is collected by the oscilloscope. As I increasing the RPM of the motor, the voltage generated by the TNG is also increasing. And when I turn off the rotary TNG, the reduction in the voltage happens. Now we will discuss the electrical characterization of the rotary TNG. This slide demonstrates the capability of rotary TNG, that is RTNG, to detect on and off condition of FM motor, highlighting its potential as a self-powered rotational sensor. Voltage output of the rotary TNG was continuously recorded using an oscilloscope, while the motor was switched on and off during the operation. In the initial stage, when there is no input, that is when the motor is stationary, and the rotary TNG produces negligible voltage output, as shown in the first region of the plot. When the motor is turned on, the rotational motion is introduced. As a result, the rotary TNG generates clean alternating voltage signal with a significantly higher amplitude. This sudden increase in the voltage confirms direct correlation between rotational motion and electrical output. The enlarged plot on the left shows the voltage signal immediately after motor is turned on, clearly indicating onset of periodic voltage generation. When the motor is turned off, the rotational motion is gradually stopping, and the voltage output from the rotary TNG decreases and returns to near zero, as shown in the right side plot. This distinct difference between on state and off state demonstrates that rotary TNG can be used for reliable detection of motor operation without any external power source. Therefore, apart from energy harvesting, the rotary TNG can function as a self-powered sensor for condition monitoring, such as detecting the operational status of rotating machineries. Now let's discuss about the electrical output characteristics of a rotary TNG in different rotational speeds. In this slide, voltage and current generated by the rotary TNG over wide range of rotational speeds from low RPM to high RPM can be seen. The top row shows the open circuit voltage, which is the voltage measurement signals, while bottom row shows the corresponding short circuit current measured at different RPM values. From the time domain voltage plots, it can observe that as the rotational speed increases, the voltage amplitude also increases. This is because at higher RPM speeds, which results in frequent contact separation and stronger electrostatic induction, leading to enhanced charge transfer. A similar trend is observed in the current signals, where the peak current is increasing with RPM. This increases mainly due to the higher rate of charge flow per unit time at higher rotational speeds. The plot on the right side summarizes the variation of peak voltage and peak current with RPM, clearly showing a strong dependence on electrical output on rotational speed. At lower RPM, the output is relatively small, whereas moderate RPM, the values of the rotary TNG produces stable and higher electrical output. At very high RPM, the output tends to saturate or slightly decrease, which can be attributed to limited contact time and dynamic effects during rapid rotation. Overall, these results demonstrate the rotary TNG a highly sensitive to change in rotational speed, making it suitable not only for energy harvesting but also for self-aware RPM sensing and conditioning monitoring of rotary machinery. Now, let's go to the demonstration of capability of rotary TNG to estimate the rotational speed of rotary machineries. Rotational speed directly from its electrical output. Due to its bearing inspired structure, the rotary TNG follows normal bearing kinematics, where rotational speed produces periodic electrical signals. As the system rotates, the interaction between rolling elements and the electrode generates a voltage signal with a frequency characteristic. So, by analyzing this voltage signal, the frequency domain using FFT, a domain frequency component can be identified. According to bearing kinematics, this dominant frequency is directly linked to the rotational speed of the system. The table shows how the RPM estimated from FFT of the voltage signal closely follows the actual input RPM over wide operating range. With increasing rotational speed, the voltage frequency increases proportionally, and the corresponding RPM value extracted from the voltage signal shows a strong one-to-one trend. This agreement confirms that a rotary TNG can reliably capture the rotational speed information without any external sensors. Therefore, apart from energy harvesting, the rotary TNG demonstrates strong potential as a self-aware RPM sensing device. So, as you can see in the table, for various RPMs from 200 to 1800 RPMs, we are collecting voltage frequency and converting to FFT, and we are getting the RPM calculation from this particular FFT. And almost with a negligible error ratio, we are getting the RPM that we are giving as an input. Okay, now we will go for a demonstration of rotary TNG.
So as we have already explained about rotary TNG and its working principle in the previous slide, so now we'll have a real demonstration of rotary TNG connected with the IoT module. So this is the rotary TNG which we already have detailedly studied about, and this is basically a testing setup. So this will be electric motor. This is the power supply for that electric motor, and what we are going to do is we will turn on this motor, and this rotary TNG will collect the data through this circuit, which is basically a circuit developed for this IoT module. So this IoT module is a ESP32, which will collect data from this rotary TNG, and it will be sent to this dashboard, as you can see, which is showing the AC voltage signal in real time. As you can see currently in this dashboard, this is almost a flat line. These small spikes are due to the noise from the circuits and ESP32. And when we turn on this rotary TNG, we will have a direct data from the rotary TNG. So as I am going to turn on this rotary TNG, as you can see, we can clearly see the spikes we are getting from the rotary TNG rotation. This data can be used for the RPM calculation, which we have already shown in the previous slide. Thank you.